for some of the work that we did ourselves, but also from the community. There is some kind of a spin orbital coupling at high temperature. Then there is a modification of the band, D band around 130, and then open it out. And eventually lead to a structural distortion and superconductivity. Okay. So since you look at all the features that has been observed, reported, it's very similar to Cooper, the ion system. So then the question, what is the material origin of this exciting, this kind of dancing, or what is exactly that is? So that's the thing we have been pursuing the last few years, try to really understand such a simple layer ion selenide, what can give rise such an interesting phenomenon. So we've been using different approach. Let me tell you what we have seen. This is a single nanowire, a very nice crystal we fabricated a few years ago. Because we think that can give us some interesting property and measure. To our surprise, okay, this is ideal ion selenide crystal. It is the perfect structure. It's not superconducting, it's insulated. Okay, so we have to look into more carefully and more detailed characterization found out this material has a ratio of selenium to iron is 5 to 4, which means every fourth iron atom is missing one. There's a vacancy. Okay, not a 1, it's a 4, 5. So it's iron 4, selenium 5. And this, if you look into this electron diffraction carefully, and you see beautiful superstructure, and that you have the iron vacancy order. This is iron vacancy order. So the detail of the TM, and then we measure the transport. There's a metal insulator transition around 30 Kelvin, and there's the vacancy, and be well described with this model. And there are two iron valence states, 2+ and 3+ in this material. You have a 4 and 5. Yeah, so the iron cannot be purely just 2+. You have certain part of the 3+ state. Yes.
Are these single crystals?
Yeah, that's a crystal. A very small, the nano size dimension. The diameter is about 100 microns. So
the layers are perpendicular to the wire. The layers are.
It's just it's interesting that the growth is just CX.
The C-axis.
Okay, so it's very interesting. But that allows us to do a little more detailed characterization, like transport and so on. Okay, and surprising, we see this. There's a lot of data. I'm just showing one of typical result. There is a strong bias frequency dependence of this transport behavior of this narrow line. Okay, when you changing the probing frequency, and the metal insulation transition seem to really change. And that has been observed in the narrow wire of iron oxide, which is a well-known metal insulation transition with a very weak transition at 125 degree Kelvin. But here is 30 Kelvin. Okay, so we see that this 4-5 has only what we still call it the very light transition in this narrow line. But at much lower temperature, which is good. That allow us to do a little bit more study. Okay, and then the questions come up: what is this? Is that connected to superconductivity? Because we know eventually this is superconducting. Okay. Well, so we decided to look into further, and in order to get a better study, we managed to make another, instead of a 1D, we make a 2D. Okay, but still very small particle. This is the 2D sheet, the iron selenium. That's the same as the 4-5 stoichiometry. and show exactly the same kind of vacancy order and has similar transport behavior. Okay, but anyway, so that's the data. But here is allow us to just simply to make some more further work to see how does it evolve from its insulating state to metallic and superconducting. And that is what happened. Okay, we anneal that kind of material at about 400 degrees or about 70, we are using 700 degrees C. You get to this one phase. You get a superconductor exactly from this vacancy order to this order state. However, you can always say because the change in the stoichiometry, what can you tell exactly what's going on? Okay, but based on that result, we know this iron selenium, the insulating plate is the insulating parent phase of the 10 degree superconductor. Well, whether there's other, okay, because in the past, people have been arguing what's the parent phase of iron selenide, and a lot of people use iron tellurium is the parent phase in doping. We prove this is not right. 4 or 5 phase is actually the parent phase, and that has the same feature as the Jupiter. It's not insulated. In fact, we have sheer data showing that not only that 10K can go up to 20K or even higher. So we decided to look into more work, but this is not it's still ongoing. Okay, ongoing. So we have started looking into different stoichiometry, changing slightly, add a little bit more, and to see what happened. And now those are some the initial power, because this is using some kind of chemical approach to do that. And then we heat treated at temperature. Then we look at by using synchrotron X-ray, high temperature X-ray, to see where they keep this kind of symmetry unchanged, or the structure unchanged, and maintain the temperature and then do some work. Okay, and we indeed see that it gradually become from the insulating, then become a superconducting. Okay, and the data also show that very nice superconducting. However, this kind of material is still not, people can always argue because they are changing this stoichiometry essentially and then make it, because it's kind of volatile, okay, and selenium, not easy to control the stoichiometry after we heat treat at high temperature. But fortunately, there is a more stable system we can look into. That is this iron 4-5, selenium 4-5 with the potassium intercalated. Okay. This has been found. This has, if you change in stoichiometry, then you get a 30 degree temp TC, or even up to 40 degree TC. But the perfect ideal K2, the 245 is the insulator. Okay. With exactly the same kind of iron vacancy order, and the extended lattice rule 5 by rule 5. But we decide to look at more and more carefully of the system to see what can we learn from here.
Where goes the potassium?
Where goes? Oh, it's in between the layer. Between the iron selenium layer. It's in between. So it's just a sort of, is a kind of a structure stabilizer. And this is interesting, all right? So we prepared a sample. This is, we call it a scrum, that the heat treat to high temperature of 245 and then cool down. And you look at the stability, nothing, impressive in terms of the characteristic. However, if you do two things, one is that I did a very high temperature and quench from that temperature down to low, room temperature. And we see magnetic susceptibility of this kind of behavior, indicating some superconductivity, although the volume pressure of the spectrum is very small. But however, on the other hand, if I do that and anneal at low temperature, without going to very high temperature, like 400 centigrade, and then slowly cool down, then it's not superconducting, it's insulated. and you see a transition of around 125 Kelvin. A lot of people argue this is iron oxide. We check very clearly. No, there's no iron oxide. It's iron selenium. Okay, take two. This is actually the same. That's well, similar to the railway transition we had. We know on the iron oxide, which means that now we can play around with this. But for a perfect 245, we know that it probably two. I mean, the order of the vacancies to rigid, you cannot really play with it. So we decide that maybe we can do a control stoichiometry by changing the iron a little bit. Okay, so we start to look at like a 4.1, 4.0 of iron, 4.2. And that's really come out with such an interesting result. But this black stuff is just a 245, you don't see anything. But if slightly changing with 4.1 with high temperature, then you get a transition. Okay, at 30 Kelvin, it's a little bit more temperature higher, then the transition become higher. However, if we this kind of material that already shows superconductivity, but I anneal at low temperature instead of going through the high temperature and quench process. Then this low temperature superconducting transition gradually disappear, and there's this metal insulate transition appear at 125 K. A long enough time, century diet. Okay. So we can really play with this material to do this following thing. You can make it superconductive, you get the sample, and then heat treat at low temperature with different time, completely kill the superconductivity, and then this material heat treat at high temperature and quench again and use it. Becomes superconductive. So you can tune from non-superconducting to superconducting with exactly this one single stoichiometry, which is nice that we can really look at what's going on in terms of this lattice structure. Okay, so that's what we have done. Okay, we have using our synchrotron light source, high temperature, to look at material that has this kind of behavior. You can really tune this volume fraction of the superconducting state by just slightly changing the temperature and look at it. And then we can study essentially what the structure would look like. Okay. Here's the interesting feature. This is a comparison of two X-ray peaks. One is that non-superconducting. The red one is the very good superconductor with a very high volume fraction. You see, all essentially the same, but there is some minor peak. In the early day, people have seen that too, and they said, "Oh, this is the immersion of a second phase." You have a two phase. You can't talk about one is state. But after we look at this with a very detailed high temperature continuous measurement, okay, or this is what we see. All right. So we go from low temperature all the way to high temperature. And this is a non-superconducting sample, and this is the superconducting sample. Just look at some of those are the typical peak, diffraction peak that associated with this changing in the vacancy order to disorder. Okay, you can see that here and here. But in the superconducting sample, if we look at these two diffraction peaks maintain the same. However, there's one shorter, but at high temperature, that shorter disappear. So it's not a second thing. It has to be the same thing. Okay? So when we, by detail analysis, this is comparison of two. So the detail is here, okay? For a superconductor, you need a lattice that continually keep the same lattice, the same symmetry. All right. For a non-superconductor, then with the vacuum disorder, then you have the always the shortest transition. That's what we have seen. Okay, on this 205, which is well controlled. Superconductivity can be, as I mentioned, can be well tuned. And this is exactly, and there are some where much higher temperatures, some kind of distortion setting. But this is essential, I think. This is what we are looking for. What kind of hall, what kind of room we need? Okay, and a little bit more detail. We could do a lot of this detailed calculation. Shows that quenching at high temperature and to maintain the high temperature phase. Okay, essentially, I mean, but the same kind of astrometry, essential. And also there is a little bit distortion of the, because what happened is this, based on our analysis, those additional heat means that the originally empty site, which is the 4D site, there are two iron occupations. One is a sitting iron, one is 4D. 4D is empty, started to be occupied by iron. And that's extra piece is the indication of the occupation of that piece. And the various vectors seem to have something to do with the distortion here. Okay, so let me just give a summary. Based on all this detailed analysis of our X-ray data, these two iron sites, 2D original in the older one is a pure 100% empty, but saying that is not insulated. Okay. Some extra iron would start to go into this actual 4D site, and then lead to essentially, if you go to high temperature, more disorder because the quenching process will keep this occupation really disordered, and that gives you some kind of metallic state, and then superconductivity is safe. Okay. And we have asked our theory friend to do some calculation, and they a very simple density functional calculation show indeed that if you have some 40 sites that to occupy, but unfortunately, you cannot really do how much the random calculate, but it's at least it's showing that indeed, when you have a 40, then the metallic state will say. Okay. So this is what happened. When we have extra iron and with high temperature processing, then this empty site starts to be occupied, and the metallic state will come in. But this is what really important for this so-called phase separation. You have two electronic phase. It's not a crystal phase. Because one with extra high 40 iron at the site you occupy, and the other one, empty site. This is two. So we have two different electronic states in this system. And a very important indication of this is that, as I mentioned, if I heat it at low temperature, okay, that kill part of this superconducting state to give you a little bit more, this is semiconductor or insulating state, like with 125 degree Kelvin transition here. Then the RT curve give you a very different result. And the transition, the superconducting transition is very different. It has a 10 degree difference in superconducting transition. Okay, so this is the perfect, very well disordered sample. We have a 31K. A less disordered sample, they get a 21K. So the competing of these two metallic and the semiconducting portion is essentially will determine the superconducting pairing. Okay. So that's why we have seen from this particular iron selenium with the application version, which is much easier to control. And we are working on this without any quotation to see if we can exactly map out the phase diagram. It's really phase diagram on iron selenium. And we believe that we have seen a couple of different PC already. Yeah, I'm almost done. Okay. So this is essentially what we understand, and now maybe that's a lead or a guideline that we can follow in the future in the next step if we want to find something new. So the summary, what we have just talked to you, we need a large enough of this standard lattice to accommodate this kind of ion vacancy in this iron selenium, okay, which is the more favorable. But which means that this allows you have kind of a mixed valence. I think cuprate, from day one, we also talk about the copper oxide. Copper has two possible states. Okay? And here, more clearly from the iron selenium, that you do have a 3+ and 2+. And that give rise this is the low temperature. When these are older, then you have this low temperature like a railway like transition. And we have to suppress this. Okay. Yeah, I have to mention that this well ordered vacancy has some anti-ferromagnetic order. It's at 200 degrees C, so also okay. And so this is the parent. I mean the starting point. And then after that, we start to fill this empty sites, and we'll make it random, right? That give you this metallic that coexists with the metallic phase and the semiconducting phase, or insulating phase, and that's some kind of a competition there, and give rise to superconductivity. And this is kind of picture of Dong-Hai Li came up in his and try to understand this iron selenium superconductivity. But this is just a model he proposed. So I believe maybe that one thing. And we have been looking for the so-called interfacial superconductivity for a long time. If that's the case, we don't know. But that's something we need to investigate further. That there are some other, for example, how this is transition changing from 30 to 20, 20, or can we go higher? I believe that you will make it even more disorder randomly, then it should be higher. Okay. So then we sort of conclude that now we have two systems. One is the cuprate, one the iron selenium. The fundamental understanding seems to be quite similar. Okay, we need some kind of empty spike. Well, this reminds me some very interesting Chinese old philosopher, very old philosophy in China. More than 2,000 years ago, the philosopher Alloul has a writing on his Alloul's chapter 11. It said, a 30 spoke meat at a half because of the hole, we may use the wheel. Clay is molded into a vessel because of the hollow, we may use the cup. Right? You don't have this kind of contain anything. You need an empty space, but clean. And then water and are built around the house because of the empty space, we may use the house. That's sure come from what exists, but used from what does not. Okay. So that's the philosophy. I think that's what we can learn from. This is a very fundamental idea. Thank you very much. People contributed.
So thank you. Are there any questions? We have time.
Yeah.
Yes. John. So as you show, the potassium doped iron selenide system is definitely very interesting and complicated.
But we are working on iron selenide right now.
Okay, but just the question I had was your argument that measuring the fraction on warming, you saw some peaks go away, which was an argument against a second phase. But to get superconducting samples, you have to prepare them at high temperature and quench. And when they're quenched, either you're quenching in a uniform phase that's different from what you would get on silicon, or you may get some interstitial layers of a different phase, which when you warm up would go away. So I guess I'm not convinced that looking at the fraction on warming and saying peaks go away argues that there's not a second set of layers, which is interesting in itself.
No, actually, yes. What we are talking about is that is a layer that start to go into the empty side. That's exactly what we are talking about here.
Right, it's just locally, the C-axis, the spacing along the C-axis may be different.
Mm-hmm.
We could give some.
Yeah, but essential is that, if you don't have that, you get the whole disorder, you have a symmetry check, but you don't. We don't have any symmetry check.
Other questions? No other questions?
I have a problem because you show two type of preparations and of measurements. In one, you're measuring the diamagnetism, and there you find that TC is independent of the treatment. It's the fraction of TC, of superconducting phase, which changes. But when you did the resistivity measurements, then you show cases with different TCs.
Yes.
So I have a problem understanding where does the difference come from?
Yeah, because you see, the magnetic measurement, if you see some component, all right, that usually you will pick up, but the volume fraction is very small. As I show in my data, when you heat treat a low temperature,
You see, all these curves.
this volume fraction will become essentially drop. Like switch the certain part which is high DC. But essentially, you have a coherent, the RT unit is a complete coherent.
The YRT is now showing something which is which depends very much of the treatment. The RT, the TC is not the same. So if you took a given sample, that you don't find the same TC in diamagnetism and resistivity.
Well, but you see, the resistivity, you want to go to really zero, right?
No. I am speaking of the onset. Onset of the drop is not the same.
We could discuss. Yeah. Any other
questions? No? If not, we thank the speaker again. We have only 20 minutes talk, if I understand.